Hello folks, we are once again back with another video of this, as I told you, that voluminous exercise, which is exercise 6.5, and now we are moving to the core application part of this application of derivatives. So we did one or two problems before this, which was also a bit of application based problems, but these are core problems. It so happened that this video was shot earlier, but there was some audio problem, so I am re-recording it, and that is why the matter is there on the board. I'll just go over it once again. So we'll just read the question and try to understand what the question is. There's a bit of demonstration that will go along with this, and then we'll try to understand this question. So first, let me read the question. Question says that a square piece of side 18 centimeter is to be made into a box without top by cutting a square from the corner and folding the flaps to form the box. What should be the side of the square to be cut off so that the volume of the box is maximum possible? Now it's all about construction of a box. So we need to construct a box from a net and then get across doing the work. So for that I have some paper cuttings. Like always, a box is made up of a net which is of this kind. You have that's a net that I've drawn here. A box is always made up of a net which is like this. Once you make a net like this, you cut it off, and from this net these squares are cut off. I hope you're able to identify. So from the net, you take this net, then cut off these squares, and that's how you will be getting a box. So these squares need to be cut off, and from here, yeah, this square, it needs to be cut off. And when from this figure these squares go off, you get the open box. As it's being told in the question, it's a box which is open at the top. So how do you get it is, after you have cut these, this is not a square box as they have told, it's a rectangular box. So suppose if you have removed these corners, then you just fold these corners like that. No, just fold, after the corners are gone, just fold that part of the rectangle like this, and you get that box. So this is how you get the box out of folding those flaps. After removing those squares on the corners and then folding those flaps, you will get the box. So this is the construction of the box. So in order to construct the box, this is how you're going to go about doing the work. Let's relate ourselves to the given problem. In the given problem, they tell that you have a square which is of side 18, all sides are 18. They allow you to cut these small squares from all the four corners and get the box. If you have got the box like that, when will be the volume maximum? That's a question. So let's go over the problem once again. We are telling that let x centimeters be removed from so there has to be some dimension which has to be removed. So we are assuming the dimension which is getting removed as x centimeter. So that means x, it's a square. So x, and that happens at all the four corners. You're removing that square which is of side x. What results is the kind of thing that I had showed you, which will have the base. And so therefore when you have the box like that, so we need to suppose if you have a box which is like this, so we need to visualize what is the length, what is the breadth, and what is the height of this box. So given this box, what is its length? Its length is this. What is its width? Its width is this. And what is its height? Its height is this particular part, this part. And what is that part? That part is x. So your length is this part that we need to find out. Your width is this part, that also we need to find out. And height we don't need to find out, because height is going to be x, because we know that these sides are x. So that much of it we know. Why we are concentrating on length, breadth and height? Because they have asked us the volume. So that is why we are concentrating on the length, width and the height. So that's about it. So that's how we reduce ourselves to this particular figure, where this can be called as a length and this can be called as a width, and your height is obviously going to be x, which you are folding. So length, why it is 18 minus 2x? Because this entire length is 18 x from here and x from here is removed. You have it removed. So when you look at this length, we have only this part. In this part, this and this is removed out of the total 18. So it is 18 minus 2x. Because it's a square, same thing happens here. So length is 18 minus 2x, width is 18 minus 2x, and height is x for the box. Okay, since we have to concentrate on the volume, let's go on to the volume. So the volume of the box is length, width, and height product. Length is 18 minus 2x, we just saw. Width is 18 minus 2x because it's a square, and height is x. So we get 18 minus 2x the whole square times x. As we know, we have to get the second derivative, the first derivative. First derivative made 0 to get the critical point, and then check at what point can there be a maximum. So we proceed. And what we do is, we try to get the first derivative, dv by dx for this. Now, either it can be done, in two ways. Like maybe you can expand 18 minus 2x the whole square, and then again multiply x, get an entire polynomial, and get the first derivative. That could be one way of doing. But that could be little, too long. Now, since you are gaining perfection in derivatives, you can treat this as a product, u times v. You can treat this as a product, u times v. That's your product, u times v, and then you can work out, the first function as it is. So 18 minus 2x the whole square as it is, derivative of x is 1. Then x as it is, derivative of 18 minus 2x the whole square. That you have to be careful. 18 minus 2x the whole square, derivative of the exponent is going to be 2 times 18 minus 2x raised to 1. That's what we got it over here. That's the derivative of the exponent. But because the base itself is a function, 18 minus 2x is a function, you have to write the derivative of 18 minus 2x also by chain rule. So derivative of 18 minus 2x is, for 18 there is no derivative because it's a number. Then minus 2x, the derivative is minus 2. So that's how you get the derivative as minus 2 for 18 minus 2x. So that's the derivative. So we have applied the chain rule, so we have got it like that. Now, if that is the case, we have put it down across here, 18 minus 2x the whole square from here. And here it's minus 4x times 18 minus 2x. For us to get the second derivative, we will expand only the second bracket. What we do is, this will expand, so it becomes minus 72x plus 8x squared. Since we have to get the second derivative, let's again find the derivative. We all know that derivative of 18 minus 2x the whole square, as we did there, is 2 times 18 minus 2x times minus 2 minus 72x derivative is negative 72, 8x squared derivative is 16x. So you get so many things. They ask us the derivative dv. So we have to get the critical point. So we are done with the first and second derivative, but we have to get the critical point. So for that we are making let dv by dx equal to 0, because we need to get the critical point. So at that time, when we restructure these, we'll see that 18 minus 2x is common throughout. So let's take it out. In the first bracket, 18 minus 2x is remaining. Second bracket, minus 4x is remaining. When we restructure it, it comes to 18 minus 6x. You have two products becoming 0, which means each of them can be 0. So you have this becoming 0 and you have this becoming 0. Wherever 18 minus 2x is 0, you have 2x equal to 18, that means x equal to 9. And here 18 minus 6x is 0, 6x is 18, x is 3. Now, there is a problem. Always when we have two values, more or less, there is generally, what we have observed till now, that there is some problem generally with one value. And generally, you just take one value and work. So also happens here. For 9, there is a problem. The problem is that if you take x as 9, then you just check this side. If x is 9, this side will become 18. So 18 minus 18, which is 0. That means your box has got 0 length and 0 width. So that's not possible, no? It doesn't make sense. So we don't take the value x equal to 9, since it's not acceptable, since L and B, or L length and breadth, it reduces to 0 when we take it like that. So length and breadth reduces to 0. Now, therefore x equal to 3 is to be considered. Out of 3 and 9, we are going to consider x equal to 3. Now, so we got actually the value, but then we have to ensure that it's maximum. So for that, we'll just check at x equal to 3 what happens to the second derivative. When we substitute the value, you definitely get a value which is less than 0. So we know that maxima occurs at x equal to 3. That's it. So 3 centimeters from the square has to be cut off in order to get the volume as large as possible. So this is a new thing, and it's been asked in the exam quite a few times. We need to know the application. It's an important application which we need to know, and then it flows. It's not so difficult. It flows very easily. So that's about the square from where the side is cut out. We have the next problem, which is exactly identical to this problem. Only thing is that it's not a square, it's a rectangle. So this was a square box. Next problem, it's a rectangular box. So with that problem, we meet in the next video. Thank you.